Hello, class. We are going to be continuing our information about engineering statics. For this lesson, it's going to cover friction, but in a slightly more advanced way than when we had it back in physics. For our example here, what we're looking at is friction being a force that always opposes an object's motion along a surface, and we'll use the symbol F sub F, capital F for force, lowercase f for friction. Now, whenever we have friction, we also have to account for a normal force, and that is the force exerted back onto an object that is on top of a surface, based on its weight on that surface. The normal force, either represented F sub n or just capital N, is always perpendicular to the surface the object is on. For example, if we have some object here with its own weight of 100 newtons pulling straight down, then the surface is causing a normal force back up onto this object. As far as for P, that stands for a pushing or a pulling force, essentially an applied force. And we also have our coefficient of friction, mu sub s, if it's our coefficient of static friction. What we're going to look at is our force of static friction. It can get as high as the following quantity, the coefficient of static friction times the normal force, so mu s times F sub n. We were told that our coefficient of static friction was 0.4, and we determined that our normal force was 100 newtons because our force of gravity was 100 newtons. Because our surface is horizontal and our normal force is completely vertical, then we don't need to worry about an x or y component of the normal force. We're assuming that our object is not accelerating along the y-axis. Therefore, whatever the amount of weight pulling down, that's what the normal force is pushing up. So 100 newton weight gives us 100 newton normal force. 0.4 times 100 newtons gives us 40 newtons as our maximum force of static friction. Now, in statics, the name of the game is seeing if the summation of forces adds up to 0. For what we're looking at right now is the summation of forces along the x-axis. Well, all we have is our applied force P, and we're going to, since that's moving to the right, that's going to be positive. Because we have a force trying to push to the right, force of friction will be pushing back to the left. Therefore, we'll make that a negative force because it's pointed to the left. P minus force of friction has to equal 0. Therefore, in order to be completely static, then our pushing force has to equal our force of static friction. Therefore, the pushing force has to also be less than or equal to 40 newtons. That means that's the most amount of force that can be applied while the object stays in static equilibrium. If instead you're pushing with 10 newtons of force, then the force of static friction will get up to 10 newtons. If you push with 30 newtons of force, then this force of static friction will get up to 30 newtons, and that will stay true up until 40 newtons. That's as far as static friction can go to cancel out an applied force. Now what we're going to look at is the example of, will the block slide under its own weight? Here what we're given is a weight of a block that's 600 newtons. Now its force of gravity, or its weight, is always straight down. But we have an example here where we have an inclined slope where the gradient angle, or the angle of elevation, is 60 degrees. Other information that we're given is that the coefficient of static friction is 0.2. Now, because of this being on a slope, we can't just say that the normal force equals the full weight of gravity, the full force of gravity. Instead, what we're going to need to do is calculate our components of our weights. Now, only for this type of example, where you have a slope, and only specifically for the force of gravity, because of trig functions, this angle is not adjacent to our weight vector. That means that if we're going to use this angle here, we'll switch and use sine for the x component and use cosine for the y component, but only for this type of scenario where you have your force and you have an angle that's not adjacent to your force. The x component of our weight is going to be pulling down our slope. No matter which direction it is, it's trying to pull the object down. Therefore, our force of friction will be trying to keep the object by pushing it up. And whatever the y component of our weight is, that is what the normal force is going to try canceling out. And by x and y, I've rotated my x and y-axis so that the positive x-axis is always pointed down my slope and the positive y-axis is always perpendicular and outward from the slope surface. Because we're dealing with friction, we need to know our normal force. That means that if it's equal to the y component of gravity, we're going to use 600 for the weight of our object's force of gravity. Now for this particular example, we're using cosine of 60 degrees for the y component because again, this angle is not adjacent to our force. Therefore, we switch using sine and cosine. And for the y component, we're using cosine just in this scenario, which 600 times cosine of 60 degrees gets us to 300 newtons. Our force of friction maximum, or this force of static friction maximum, well, we'll take our coefficient of static friction, 0.2, multiply it by our normal force of 300. Our static friction can get as high as 60 newtons and can cancel out any force that is 60 or less. Now, if we look at our x component of gravity, again, for just this type of scenario, and just for the weight of our object, we're using sine for the x component. Well, we have 600 multiplied by sine of our angle of elevation, sine of 60 degrees. That comes out to 519.6 newtons. Under this scenario, Wx is greater than our static force of friction's maximum value. Under this scenario, the block will slide under its own weight. Now let's see what p-value is needed to prevent the block from sliding downward if we're essentially pushing parallel to our slope, so we don't need a y or x component. We are just pushing our object. We still have our object's x component of weight pulling down the slope. We still have the force of friction trying to keep the object from falling down the slope. How much pushing force do we need to basically balance this? Well, we have our weight x component being 519.6 newtons. We have our maximum force of static friction being 60 newtons. Therefore, the summation of forces in the x direction have to equal 0. We're going to have our applied force plus our force of friction's maximum value minus the weight in the x direction, all that has to add up to 0. So in other words, what's going to happen is the weight in the x direction minus the force of friction's maximum value will be 519.6 minus 60, which equals 459.6 newtons. And that is what is necessary to prevent the object from sliding downwards. If these two forces are in play, then pushing with a force of 459.6 newtons will prevent Wx from overcoming the maximum value of the force of friction. Now, I have mentioned in the past that going down our slope is our positive x-axis, going up the slope is the negative x-axis. The reason why I have P as positive and F sub F max as positive, realistically, that's because in the end I just want the magnitude of my applied force. So I just did things in a way so that I could get its value. I know it's going to be in the negative x direction or against motion along this slope. Now, here's an interesting thing. If we start pushing with more force than 459.6 newtons, then in reality, our force of friction will invert and we'll actually be trying to pull our objects back down the slope along with our x component of gravity, Wx, if our applied force is pushing more than what's necessary to cancel out from sliding down. So to figure out what is our maximum applied force, or P max, that can be used before the block would start sliding upwards, well, now we want to have the summation of forces in the x direction equaling 0. We have our P maximum minus Wx minus F sub F maximum equaling 0. Adding both of those to the other side, what I essentially have now is my applied force maximum value can be as high as Wx and F sub F max. That adds up to 519.6 plus 60 newtons, or 579.6 newtons. Once we start pushing with more than this force, so say 580 newtons, the block will start sliding upwards. Therefore, we have this sweet spot where if we are effectively pushing anywhere between roughly 460 newtons and 580 newtons, then this will still allow the rigid body to be in static equilibrium. So what I have here is roughly 460 newtons less than or equal to P less than or equal to 580 newtons. That means that if we are pushing with anything between those two numbers, then our object, the weight in the x component and the force of friction are going to interact in such a way that we're still going to have our object in static equilibrium. Now, let's look at a situation where we have two objects stacked on top of each other. On the left side, what we have here is object 1 of 100 newtons of weight existing on top of object 2, where object 2 is 200 newtons. Object 1 is tied to the wall. Therefore, if we start pushing on object 2, if it slides, object 1 is not going to slide, or it's going to stay still in its current position as object 2 slides. Now the coefficient of static friction, mu sub S1, that's between object 1 and object 2, that's 0.2, and the coefficient of static friction, mu sub S2, That's between our bottom object and the surface. That will be 0.4. Let's try to answer the question, what applied force being pushed to the right directly onto object 2 must be applied to move block 2? Well, first thing we're going to do is we are going to completely isolate block number 2. It is going to have the following forces. If some applied force is trying to push or pull object 2 to the right, then there will be a force of friction between object 1 and 2, F sub F1, that's pushing back to left, trying to stop the block from sliding to the right. Also along our surface, F sub F2, a force of friction that's also pulling to the left, trying to prevent this object from sliding to the right. We will have weight number 2 pushing down on our surface, and our normal force, F sub N2, pushing back up on our surface, pushing back up onto our block. And then at the interface between our two blocks, we have the weight 1 pushing down on the top of our block, and the normal force, Fn1, between the two blocks, where block 2 is pushing back on block 1. Well, let's calculate those values. F sub N1, that's going to be 100 newtons because object 1 is 100 newtons, or I should say the top object is 100 newtons. Weight 1 is pushing down with 100 newtons, therefore the normal force 1 is pushing back up with 100 newtons. F sub F1 is the coefficient of static friction times the normal force, so 0.2 times 100 newtons. The value that we were given and the one that we determined, that gets us to 20 newtons for our force of friction between our two blocks. F sub N2, the normal force, well, that's the entire weight that is on our surface. So not just our 200 newton block, but also the 100 newton block as well. So that adds up to 300 newtons that is on our surface at the ground level. Force of friction 2, therefore, is going to be 0.4, or whatever value we're given, multiplied by 300 newtons to equal 120 newtons. We're just thinking about moving along our x-axis. Therefore, summation of forces along the x-axis have to equal 0 for us to be under static equilibrium. We have our applied force minus our force of friction 1 minus our force of friction 2 having to equal 0. Adding those two to the other side, we have our applied force equaling 20 plus 120 newtons equaling 140 newtons. Therefore, we can push or pull to the right with a up to 140 newtons, and the block will still be under static equilibrium, and it will not slide between our surface and block 1. This is called an example of impending motion at all contact points. Essentially, because block 1 is tied down, it's not going to move to the right as block 2 moves to the right. It's going to be stationary in the air as block 2 is grinding against the surface on the ground and block 1. So every contact point, there is a potential for impending motion. A completely somewhat different situation is impending motion at some contact points. What we're going to assume in this scenario is that assume sliding at one surface and then confirm if force of friction 1 is less than or equal to force of friction 2. This happens if we have a block resting on a second block where the top block is not tied down to a wall. We're looking at our similar situation again, but without being tied down. We have some applied force pushing on top of our top block now, pushing to the right. Block 1 on top is 100 newtons. Block 2 on the bottom is 200 newtons. The interface between the blocks has a coefficient of friction of 0.2. The coefficient of static friction between the bottom block and ground is 0.4. We're going to break these into two sets of free body diagrams because they're now independent. We have block number 1 that has an applied force to the right. If it slides to the right, then it will have a force of friction along our block-block interface, pulling back to the left. We have 100 Newton weight, its own weight, pushing down, so we have a normal force F sub N1 pushing back up on the top block. Balancing our forces in the x-axis so that the summation of F sub x equals 0, well, that means P, the force to the right, minus F sub F1, the force to the left, has to equal 0. Adding our force of friction to the other side, P equals 20 newtons. Now, let's look at our second free body diagram for our second block. We have the force of friction F sub F1. Now, though, we're trying to assume that that block 1 is not moving at all on top of block 2. That means that we're actually going to invert F sub F1 in this scenario. When we look at block 2, F sub F1 is pulling back to the right. Object 2 has a force of friction between it and the ground surface that's still pushing to the left of F sub F2. It has a weight 2 that's pulling down, which is the total weight of our system, the 300 newtons. Therefore, the normal force F sub N2 is also 300 newtons, pushing back up. Using our coefficient of friction, 0.4, F sub F2, or the static friction between block 2 and the ground surface, that would be 0.4 times 300 newtons, equaling 120 newtons. That passes our check, where F sub F1 of 20 newtons is less than or equal to F sub F2 of 120 newtons. Under that scenario, if we ever push with enough force to overcome static friction, we're gonna move object 1 before we ever move object 2, because once we overcome that 20 newtons, object 1 is going to start moving, and not object 1 and object 2. This means that only block 1 will slide, and our initial assumption is correct, that the force of friction 1 is less than or equal to the force of friction 2. We push with enough force to overcome 20 newtons. Only block 1 will start moving while block 2 stays still. Now let's look at this scenario where we actually invert our blocks. So now that the top block, number 1, is actually 200 newtons, and block 2 on the bottom is now 100 newtons. Well, between those two blocks, the coefficient of friction, mu sub S1, will still be 0.2, but now between the 100 Newton block and the ground surface, perhaps it's a different type of material than block 2 or the original block 2. Therefore, our new block number 2 of 100 newtons has a coefficient of static friction of 0.05. Let's redo our calculations again though, where we have our free body diagram as independent blocks. Block 1 has F sub F1 pulling to left, our applied force pushing or pulling to the right, weight 1 being 200 newtons pushing down, so normal force number 1 will be pushing back up with 200 newtons. For weight number 1, that arrow should be pointed downwards. But F sub N1 is pushing back up. That'll be 200 newtons. If we look at block number 2, we're now going to have F sub F1 pushing back to the right, F sub F2 on the ground surface pushing to the left, weight number 2 pushing down. For the total weight of our system, 200 plus 100 being 300 newtons, and F sub N2 being 300 newtons, pushing back up. The first force of friction will be 0.2 times 200 newtons, or 40 newtons. Now we need to see if F sub F1 is less than or equal to F sub F2. In which case, we can still be under static equilibrium if P equals 40 newtons, up to 40 newtons. But now, if we calculate F sub F2, that will be 0.05 times 300 newtons. That gets us to 15 newtons for F sub F2. Because F sub F1 is not less than or equal to F sub F2, our assumption of the surface of motion being the interface of the blocks was incorrect. So we should redo our problem along our second surface, the bottom block and ground level. Now our free body diagram includes both blocks, the top 200 Newton block, the bottom 100 Newton block. We still have our pushing force pulling to the right on block number 1, or the top block, the 200 Newton block. On the bottom here, we have our bottom block of 100 newtons. The reason why we are now assigning F sub F1 as between the bottom block and ground surface is because this is where we are assuming there is going to be motion. So we have F sub F1 pulling to left. The entire weight of our system is 300 newtons pulling down. Weight 1 is 300. So normal force number 1 is going to be 300 newtons pushing back up. Between our two blocks, we have force of friction 2. That's both pulling to the left to counter our applied force and pulling to the right to stay on top of block at the bottom. Looking at this, F sub F1 will be the coefficient of static friction between bottom block and the ground, 0.05, times the total weight of our system, 300 newtons. F sub F1 therefore equals 15 newtons. Under this scenario, F sub F1 is going to equal F sub F2 of 15 newtons. The reason is because in our prior example, we were able to determine that between the blocks, the force of friction is not less than or equal to the maximum force of friction between the bottom block and ground. So if we push with just enough force to overcome the bottom friction, our entire thing is going to start moving, and not just our individual top block. Which means that F sub F2 in our case is only going to get as high as whatever F sub 1 is before it gets overcome. So the summation of forces in the x direction has to equal 0. We are just looking at our top block now. We have our applied force to the right minus our force of friction 2 pulling back to left equals 0. P equals 15 newtons. Both blocks will move together if we go past 15 newtons of force, because at that point force of friction will no longer cancel our applied force under our system of some contact points of impending motion. In any case, that is our lesson for friction. Pretty glad to have you all in class, and if you're not in class with me, glad to have given you this lesson today. For those of you outside of my class, if you would like to like the video and subscribe to the channel, I like saying that because it makes the subscribe button turn all rainbow color. But in case you don't actually have to do that, I wish you all the best and look forward to seeing any comments if not, but in any case, see you all in the next lesson. Peace.